Hello, class. Today we are going to write equations of tangent and normal lines. So, previously, we learned that tangent lines can be used to estimate the rate of change on a curve. So here's some examples of tangent lines. You have more examples of tangent lines earlier on in your notes. So we have all these tangent lines, tangent lines, tangent lines. If we find the slope of a tangent line, it tells us the instantaneous rate of change at that point on the curve. So if I want to know like the instantaneous change at this point right here, I would look at the slope of the tangent line, which would tell me that the instantaneous change, otherwise known as dy dx, is equal to 0. Okay, so if we want to know the equation for a tangent line, there's a few things that we're going to need to do. For one, we're going to need to find the instantaneous rate of change at the point, because that is going to be the gradient of the tangent line. So let's start with that. So to find the instantaneous rate of change, we need to find the derivative, otherwise known as dy dx or f prime of x. So looking at our original function given to us, f of x equals 0.5x squared minus 2, first we're going to find the derivative of that. So I can write f prime of x equals, then I'm just going to use my derivative rule, my power rule. So I have 2 times 0.5. I just did my exponent times my coefficient, x to the power of 2 minus 1. And then this minus 2 term, this is a constant term. And if you'll remember from the previous lesson, constant term just changes into 0 when we take the derivative. So let's simplify this. F prime of x equals 2 times 0.5, that's just 1. So I have 1x, and then 2 minus 1 is 1. And then the minus 0, that basically doesn't change the value, so I don't even have to copy that down. Okay, I can simplify this even further because 1x to the power of 1 is just x. So this is my derivative of the function. So now, since I want the tangent line when x equals 2, I specifically want to know what is the instantaneous rate of change at x equals 2. So I'm going to plug in 2 for my x in my derivative function. So everywhere I see an x in the derivative function, I'm going to replace it with a 2. Okay, so this is telling me when x equals 2, the instantaneous rate of change, or the dy dx, is equal to 2. Okay, so this is going to help me write the equation of my tangent line, because this is the instantaneous rate of change is the gradient of the tangent line. So now, I'm going to use that gradient, and I'm going to use the point of tangency in order to write my equation. So first I'm going to write down the equation of a line. Y minus y1 equals m times x minus x1. And then now I'm ready to plug in my values. But first, so we already said the gradient is 2. But let's figure out our point. So we want when x equals 2, so I know my x value is 2. And And then we can look at the graph to see, okay, when x is 2, y is 0 on this function. The other way I could have found this y value here is I could have used the original function that the problem gave me. So the problem gave me the function f of x equals 0.5 x squared minus 2. So I could have plugged in 2 for x. So I'd have f of 2 equals 0.5 times 2 squared minus 2. If I put the right side of this equation in the calculator, I would get 0. Which tells me that the y is 0 when the x is 2, which matches up with this point that I see on my graph. So now I know my point. I'm going to label my point x1 and y1, and I'm going to plug it into the equation of a line formula, the point gradient form. So y minus y1, so y minus 0 equals m, which is 2, times x minus x1. x1 is also 2, because that's the x value of the point. And now I can simplify. So y minus 0, well, that just simplifies to y. And then on the right side, I can distribute. So I have 2x minus 4. All I did was I took that 2 and I multiplied it by everything inside the parentheses. Okay, so this is the equation of my tangent line. And if I come over to my graph, I could draw my tangent line. It's going through this point we already know, and we know it has a gradient of 2, so I can go up 1, up 2, over 1, and then I can just do that in reverse, so down 1, down 2, left 1, and if I connect the dots there, I have graphed my tangent line. So now let's write the equation of the normal line. So the normal line is very similar to the tangent line. It's just perpendicular to that tangent line. So it's going to be the negative reciprocal gradient of the tangent line. So if the gradient of the tangent line was 2, the gradient of the normal line would be negative 1 over 2. Because I have to switch the sign and flip the fraction. Okay, the point that it's going through is still the same. So the point is still 2, 0. So that's my x1, y1. So now I can just follow the same process. Y minus y1 equals m times x minus x1. But instead of using the tangent gradient, I'm going to use the normal gradient. So I have y minus 0 equals negative 1/2 times x minus 2. Simplify, I get y equals negative 1/2 x. Negative 1/2 times negative 2. Negative times a negative is a positive, so I have a plus sign. And then 1/2 times 2. 2 halves is just a whole. It's one whole. So it's just 1. Okay, so this is the equation of my normal line. So now I'm ready to graph that normal line. So we know we're going through this point, P, and we know the y-intercept is 1, so I can graph that, because this is our y-intercept. Y equals mx plus c. C is the y-intercept. And then my gradient, negative 1/2, tells me I go down 1 over 2. Down 1 over 2. So I can now connect the points that I plotted. And looks like a 90-degree angle to me. And it's still going through that point when x equals 2. So we can feel pretty confident that we crushed it. Alright, y'all. I uploaded lots of hints to the Edulastic. And I will be at school on Monday to answer any questions. I will not count it late if you turn it in on Monday. The Edulastic. So just try your best. Bring your questions on Monday. Peace out.